I think the talk is now really close to being obsolete, thanks that the ITEC is so fast. City heater, I don't know if that's correct in Slovenian. And I want to speak about a bit what we did, Günther and I did. And I tend, let's get a step back and to think about what we're actually doing with BPMs. BPMs, this instrumentation. If you think what people did when they wanted to measure, find out, are horses airborne if they're doing gallop? And what they did, they used a lot of these cameras here. And if you go back, you see here down the trigger lines that the horse would trigger. And in the end, what was interesting is that you could produce this set of photos. And this set of photos, and if you look to here to this graphics up there, that show that the horse is really airborne at the gallop. And basically what you did, you had single instruments, you combined them together in a triggered fashion, and then when you combine, you can do the analysis. And actually what I see today is that these instruments are very much elaborate, but what we have to do on the user side needs that all this data are combined in a consistent fashion. So what Günther said already, and what I always like to do is take a step back and look to the instrument what they are. And if you start, if you know stroboscopes once upon a time for measuring RPM, you had some pattern, you would flash at it, you would tune the flashing, you would find out how fast it turns. The other way is if you do an optics lab and you do optics measurement, you take a piece of paper and go along the beam and you find out what it is. Unfortunately, we can't do this with BPMs, we only have a few. Position-sensitive devices. Why I like to think about them. Position-sensitive devices give you two voltages. You trigger them on an oscilloscope, and you get all what you need. Of course, in such a fancy system, it's not that easy. If you ask what a beam people say, yeah, we want to know have the position of the ring along the ring, periodically updated. What I like to call like a line camera. Because you're doing one line after the other, and then you basically let it go through like a CCD, and you get the time evolution. And for control, it's simply a regulation input. When is the input useful? One never should forget the first thing, that we get reliable data in a consistent manner across the ring. And it's nice if they're fast, but the first two have to be fulfilled. Günther says, all of you know, it's the input or orbit stabilization, standard practice. But now we have a new kid on the block, it's called machine learning. And in machine learning, for example, reinforcement learning, you need to do something like 50,000 steps. You're able to run that with a 10 milliseconds range, you do it something like 100 seconds. If you do it in a 2-second range, is something an excuse for a long lunch. And then there's one more thing which is popping up, a streaming approach. You have a stream of data coming in, and you have reactions going back, and that all needs consistent data. What does it mean, consistent data? And I will come to the end of the slide once more to iterate it. Consistent data, what is critical is the data model, and nicely you have that internally. I have an example here, what my colleague and I really worked on is how you can consistently present the data from the BPM on the different measurement points to combine it for the BPA measurement. And if you go over, let me see, we have the BPM element, I mean that's what the old system is, and we go back, we have the measurement points, the measurement, and we go back and come back to the end. So we need an intuitive schema, we need sub-data models, pre-data types, and the point is what I want to make is we have that already on the system side, and now the interest would be to have this point all over the control system in a consistent fashion, because then you don't need to know at which stage how it's represented, because it's represented already consistently in the whole system. So what's the step? We have already the atomic data, I think you call it atomic data, the XY position, the time count. EPICS7 splits it up. That you already have it now in V7, that we have normative types. And the normative types would really allow to expose it, what you have internally to the EPIC system. Then we combine them, there's the collector, combine, accumulate, and so on. And then we have the data in a consistent fashion that we can see all the different BPMs as a line system, a line camera. We have the combined data that go to input regulation, that go out. It's convenient for data taking, and don't forget the new kid on the block. Lastly, let's talk about, I don't know if you heard about Bluesky. It's this data experimental orchestration framework. Again, what we do, I mean, we have that in a vector, and we have to disassemble for the old system, but now it's really, we have IDs, we have what I like to refer as a payload, X and Y, that we combine. We have the data model. If you have it in control, if you have it on the instrument, we have it on a control system, we can do it consistently down here on this layer. And then in this layer, because we have the run engine, which produces event documents, and these event documents get into the database. The end is, I have already a data model stored in this database. If you look into it, if you have a newcomer, you say, okay, that's our data, that's the measurement points, that's the BPM data, it has the name, it has the position, and so on, and it has the ID, and that is all in a consistent way. And then it makes it much more easier for the next steps, which is the application framework. Well, do you need the naming? Because if you have the BPM 1, 2, 3, 4, 5, why do you really have to name into there? And I'll give you an example here. Well, we tend to call our children by name. I don't have much, but you know, the Romans, you know, there's the name Sixtus and so on. They sometimes will just count the children. I don't know why. But, you know, it's really practical to have namings, because what I want to show here, we have here what you need for local. One is the data which you get out of the model. You forecast what the step you would have. And the other one is what you can get out of the machine. And we had an error where an old combiner by ID of 1, the consistence difference between the machine and the data. And if you zoom in, where we don't have too much phase advance in the Y, because it's only 6.8 tune advance, then you can really see that that's the error of being off by 1. Here in the X, where we are 16 or something at tune, you won't see it. And for the new machines, it will be even more difficult. It's nothing fancy to track down, but it takes time. I want to give you a comparison. If you do magnets and the magnetic measurement, you always can do conclude which polarity they have from the measurement. But still, it's good practice to use a polarity meter, which is something like a compass, as simple as possible, that you're sure you have your polarity right. And I see that to have a consistent naming in that fashion again. So what's brewing? Well, we learned to build the IOC. It was pretty straightforward. In the virtual box with the Bodman image, we could do it with version 3.24. I think there was also version 3.2.6 where I didn't succeed. Towards EPICS7, PV-based, combined on Sparkbox. We have dedicated records now. I mean, you have dedicated records. We have a consistent data delivery. We could find out that we see a monitor with client timestamps, that it was delivered consistently, but we have a bit of a shit of network delays. We started to investigate if QServe2 is solving that. Heinz Junkers recommended it to us, but that's work in progress. So, long story short, Libera IOC, so we can combine data to the VAC. We do it based on the identifier, so we get a consistent data set, whatever happens along the network. Towards EPICS7, we could really have the very early stage, the data model represented by the data model that you already have. We have a consistent data model in the control system, in the measurement, in the analysis, in the storage. And that supports combination. So we start from a single pixel to a line camera. And I think there's something else that I suppose would become, here we're talking about the BPMs for the electron ring, there are BPMs for the X-ray rings. I'm just waiting that someone would say we want to combine that. So that we really could have an integrated system that works on stabilizing the image or the location or the light for where it really matters at the end of the beam line, X-ray beam line. So that's from my side. Thanks for your attention.
Thank you very much. Do we have any questions?
A curiosity, because I had a problem like this for the web scanner of ESS.
Yes?
In order to be sure of the relationship between the different samples acquired over the propagation along the limit.
Okay.
And we used the external triggering system based on the event generator.
Yes.
With a
Yes.
random counter maintaining the difference between each acquiring station in order to be sure that we are not using any shot. But in that case, the repetition rate was some hertz. 10,
Yeah.
There is any kind of limit on the real time or the ability to follow the acquisition without losing data?
Yeah, but currently, you see, currently we are slow. It's on the slow side. It's a 10 hertz side that we're working on. The point is really we have glitches in the network. As soon as you have the identifier in the packet and you're sure you have a consistent packet, you arrive. And then the nice thing is, I will only get data if I have a full set or deliberately excluded. Yeah?
Okay.
And then the user will feel if I don't deliver. So I have, in this way, manner, I have an assurance that I have consistent data. And I would like to say first consistency, then the high rate.